Why is induced EMF critical in understanding Faraday's law? Have you ever wondered how electricity is generated from magnets? The answer lies in the concept of induced electromotive force, often referred to as induced EMF. This principle is at the heart of Faraday's law, which describes how a changing magnetic environment can create an electrical effect in a conductor or coil. Faraday's law states that when there is a time-varying magnetic flux through a circuit, an induced EMF is generated. This induced EMF can drive an electrical current if the circuit is closed. So, why is this induced EMF so important? It is the measurable electrical output that shows the interaction between magnetic fields and electric circuits. To understand this better, let's break down the concept of magnetic flux. Magnetic flux is the measure of the magnetic field passing through a specific area, like a coil of wire. When this flux changes, whether due to the movement of a magnet or changes in the magnetic field strength, Faraday's law tells us that an EMF will be produced. The amount of induced EMF is directly related to how quickly the magnetic flux changes and the number of turns in the coil. The formula for this is EMF equals negative N multiplied by the change in magnetic flux divided by the change in time. Here, N represents the number of turns in the coil, and the negative sign indicates that the induced EMF opposes the change in flux, as explained by Lenz's law. From the viewpoint of electrical engineering, grasping the concept of induced EMF is essential. It explains how electrical energy can be generated or transformed from magnetic energy. This principle is fundamental to the operation of many devices, including transformers, electric generators, inductors, and motors. For instance, in a generator, mechanical motion alters the magnetic flux through coils, resulting in an induced EMF that drives electrical current. In transformers, a changing current in one coil creates a changing magnetic flux that induces an EMF in another coil, allowing for voltage transformation. Furthermore, understanding induced EMF is vital for analyzing and designing circuits that involve changing magnetic fields. It helps engineers predict voltage outputs, design efficient energy conversion systems, and comprehend transient behaviors in electromagnetic devices. Without the idea of induced EMF, applying Faraday's law in electrical engineering would be impossible, as it connects magnetic field changes to electrical circuit responses. In summary, induced EMF is critical for understanding Faraday's law because it represents the direct electrical result of changing magnetic flux. This understanding enables the prediction and application of electromagnetic induction in various electrical engineering scenarios.